Okay, let's go ahead and talk about this question here as a warm-up. So we are looking for the region from 0 to 2 under the square root of x, from x equals 0 to x equals 2. Ignore the purple circle, and so revolved about the y-axis. So step 1 is we're supposed to draw a rectangle in here. And then we're going to use that rectangle to decide is it dx, is it dy. So you'd already said to me that you think this is dy, which means I should draw the rectangle horizontally is right. So I'm going to draw in a little horizontal rectangle here. And remember that this is a random rectangle. And notice again there's that perpendicular thought sitting right here, right? So that's going to mean it's a washer. So off to the side here, I'm going to draw my cross section. Okay. Now, when I'm thinking of the equation, like this equation is really y equals the square root of x. Is that in the correct, is that solved for the correct variable or not? It's not. So, because the moment I've drawn this horizontally and I think about step 3, like it's got to be the integral of dy, which means x needs to be solved for to get y stuff. So x is going to be y squared. So when you think about that x distance, though, it is not the radius that you might first think it is. Like sometimes people look at that x equals y squared and they think that somehow the green is corresponding here to that. It's really not. So where is y squared in this drawing and this drawing? Sadvika. It is the radius of the inner circle, so this distance from here to here is actually y squared. Now, where is that same distance over here? Be more specific. Along the red how or where? The y value, I don't think you wanted me to think that. From where to where? Yes, so from the axis here to the point. So this distance from here to here is actually what y squared is. So when you think again about the washer method, we needed the big radius. Well, what is the big radius over here in this drawing? So what is that big radius? Somebody else tell me. Faith? So the radius, though, is 2, yes, and so it's just always 2, isn't it? This further distance here happens to be a constant, which means on the outside of this three-dimensional shape, you notice it would give the impression of a cylinder. It should look like a cylinder because there's this notion of constant. Right, the outside radius is always the same. Okay, so when I think about my answer here, I'm integrating dy. Again, I tend to put the pi on the outside, so pi big radius squared minus little radius squared. And there's already the pi there, so don't include a second one. So far it should have something that looks like that. Oh, I forgot to square it, sorry, squared. That's really easy to do because it already looks squared, so you feel like you already squared it, but you didn't square it yet because that's just the radius. If this value from here to here is 2, isn't it? So if we're looking for that area, so it should be pi radius squared. Got it? Siri? Sadvika? The one Sadvika said? Sadvika, why again are you calling the little radius here y squared? Can you tell Siri what you're thinking? It might also help to remember, Mason, going back to what you said on Friday. So if I go here, Mason, and ask you, where's the y-axis? Where is it? Coming where? At you, yes. So if this is the y-axis coming straight out, notice that we're going from the y-axis to the nearer spot. So from the y-axis to the nearer would be here. And if you think about this as a function, we usually think tell it x, it tells us y. We are now telling it x, and we're telling it some x value, thinking about how this y is connected in the other direction. So this is an x value. What is x? Y squared. So that must correspond to the radius over here. Limits now. Lower limit. Upper limit. Yeah, don't say 2 there. It's definitely the square root of 2 because it's the y value again, right? We need to solve for what that y value is. Put in your calculator. I didn't do that. Did you? It gave you some decimal. Does the 89 give you a fraction? What did it give you? I think with the square root in there, Brian, like it won't, the 84 won't do it. I will say this, so for decimal answers, you need 3 decimal places. 3 decimal places to be considered accurate for the AP test. I'm going to do this problem in a new way. Are we okay with this answer? Old news? What if I really want to integrate this dx? Okay, same region, same revolution, but I want to integrate it dx. Okay, that's going to be where I'm starting this thought. So really with this shell method, what's helpful is that it's really going to be another way, another perspective to get the same answer that might be easier in some circumstances. So it really is the case that you should be able to do either washer or shell, and it's just going to mean some differences of the calculation. So first, if I want to integrate this dx, how would I have had to draw the rectangle here that I'm revolving? It's got to be up and down, so I'm going to draw that in. So I'm going to draw in some vertical little rectangle here. Again, isn't the change in x for that rectangle dx, right? It's the width there is the dx, so again, there's the reason. Now, here's one thought as to why this is an easier, or could be easier in some situations. We actually know the limits right now with no work. The lower limit is still 0, but what's the upper limit? It's got to be 2, right? Do you see that by switching to dx, we've made the limits actually here really easy? There is no solving, there is no rearranging, because I'm stopping at x equals 2. Now, there is an issue though, because so I've drawn my rectangle, and I've really skipped my step 2, which is supposed to be up here. I'm supposed to draw that cross section, right? This is a very different shape. So if I take a segment and revolve it about a parallel line, we mentioned this a little bit the other day. So imagine a vertical segment, vertical line, and I'm going to spin it. Maybe think about it on edge. Like think about the shape that's made. So if you're looking down from it from above, you actually just would see like a circle, okay? But in 3 dimensions, it's not really a circle. In 3 dimensions, it would be this. It would kind of look like a cylinder, except it's not. It's really more like there's a tiny little thickness here that as it sweeps about, and it's going to make, and here's our name for today, It's called a cylindrical shell. It's really the shell of a cylinder when we think about it. There is a hole here, right? This is totally empty. I might encourage you to think about it like a pipe or a hose or a tube, right? That's really what we have. We have a thickness to the wall of it. Now, I do have this as a little bit of an animation to help us see it back here. So I've already actually started, I just paused it there, but I started to revolve it. So this is what you're kind of doing. So I'm going to draw some rectangle in. As I revolve it, can you kind of see the pipe, the tube that was made? Now, it looks more like a cylinder minus a cylinder almost, doesn't it? But when we think about the width of it, the width of this rectangle, isn't this approaching 0? Which means the thickness of the wall of this tube should be approaching 0, which is why, again, it's the shell of a cylinder that we're making. I'm going to make a few more here. And you notice that I could build a three-dimensional shape this way. Yeah, we'll be there in a second. Okay, so here's my other analogy. Suppose I take a sheet of paper. A piece of paper is a good image here as we think about a cylindrical shell. So if I fold the ends together, I can make kind of my tube, right? So here's kind of the thing that we're making. So think about, I could build a three-dimensional shape by taking some paper and tape it like this. And then I cut a sheet of paper down a little bit or make it a little bit bigger and wrap it around and tape it. And then a little bit taller sheet and wrap it around and tape it and wrap it around and tape it and wrap it around and tape it. Do you see that's kind of like stacking CDs or DVDs when we think about that image? We're going to build it up by wrapping it with another, well, shell. As I continue to watch this, like it's producing, I hope if you look at it from another perspective, you can almost see the washers that we were doing before, right? Isn't there really going to be an outer and an inner here, like as this shape is starting to form? Okay. Like the washers would really be like, if you think about going all the way over here to 2, right? Like this is really the whole, and we're thinking of this other region here that would produce the rest of that washer, but I'm eventually going to get that filled in as I continue to make these shells bigger and bigger. Now, so when I think about drawing this cross section, so back here in OneNote, when I think about drawing my cross section, this is not maybe as helpful as drawing the paper. So I'm really thinking about that kind of image there is like my paper folded up, you know, like in this state. Now, when we think about what we're trying to do, we're trying to calculate the volume of the shape, right? So when I think about my paper like this, I could think about, well, it's kind of like a cylinder minus a cylinder that's almost the same size as the previous one, right? That's really what's happening here. So the question isn't how much can this shape hold. This is the most important thing I'm about to say. The question is not how much can I fill this shape with. The question is how much paper is in my hand. Because when you think about volume, like we're trying to create the volume of the shape. So if I take paper and I wrap it up and I wrap it up and I wrap it up, the end of the day, the volume of the shape should be the amount of paper that's used, not anything about the size of the hole in the middle, because the size of the hole in the middle could be filled by other sheets of paper, right? So when you think about this image, it's less helpful than to actually think about cutting the paper and unrolling it and think about it in this image of like a slab. So think about cutting this shape, unfolding it, you would get this kind of rectangular prism. I drew that badly. And I really want to calculate the volume of this. In some ways, it's really the notion of the area, though, as well. So maybe that's to stay consistent. Maybe I'll think about area. The reason I'm going to say area is because the thickness of it is supposed to be going to 0. Do you notice that we've actually already accounted for that? This little thickness right here should be the thickness between the walls, which is dx. Okay, so what's the area here? We need to think about this shape unfolded to get that shape. One dimension is definitely the height of this shell. That's sitting right here. And then this dimension should be, well, it's the cylinder shell unfolded. So think about like if I take a soup can and I cut the label and I unfold the label, doesn't the label then tell me the circumference of the can? So if I cut this and unfold it, this distance should be circumference. Let me pause. I don't know if I said that awesomely, so if you have a question, anything I've said, want me to say that again or say that differently, I will. Anything I've said so far not clear about how we're creating these shells? Think about, like, if I zoom in here, like, so this thickness here, there's actually still like 2 radii, right? When you think about like the washer method, there was an inner radius and outer radius. So the inner radius would be right here. The outer radius would be on the other side of that rectangle, which is why we're getting something with a really thin wall to it. So that thickness here of this rectangle should correspond in this image of the thickness of the shell. And when you unfold it, it should be like this dimension. And that dimension is the dx, which is part of our calculation here, and that's why I'm still needing the rest of the area, which is this surface area of that piece there. Okay? Anything else people want to ask about? I'm going to keep going. So we're almost done. So I'm going to go back here. So there's the height. This distance from here to here. Now, I just kind of said that there were 2 distances, right? Like to get that thickness. But isn't that thickness going to 0? So in essence, isn't there really 1 distance from the y-axis? So I'm going to call this distance like r. I'm calling it 1 distance because, again, that thickness should be going to 0. The reason I'm wanting r is because I need that for the circumference, don't I? So the circumference of the shape is what? 2 pi times the radius. Okay. So we have all the pieces now we need. So there's a 2 pi. I need radius, and I need height. The height is probably the easier one to think about. Like the height is definitely defined by the function, isn't it? So the height here, now we've already decided dx, so we can just put the x value or the y value of x to the half in. Right, that's what we have. And that should be this distance, so that's really the square root of x. So notice that that's true for every x between 0 and 2. Right, the height will be the square root of whatever that x value is. The radius sometimes people get confused about, but it's actually really simple. When you think about where I'm marking it, do you notice again that this radius is not constant? it's always going to be some number between 0 and 2, right? Isn't there going to, I could have drawn this rectangle or this one or this one or this one or this one. But in general, the radius is always just what value? The function minus the initial point. When you say the function minus the initial point, I'm not sure what you mean. You actually just told me this again, right? So root x minus 0, you're actually looking in this dimension. Root x is a y value, so it'd be the top where it's meeting the red. The 0 is actually the x-axis because it's dx. It's easier even than that. You're warmer. You're colder. Tell me what to write, Siri. Tell me what to write. We're just going to write x. Isn't this just whatever x is? Now, again, it's really natural to get stumped by that, I think, at first, like most students do. They're like, I don't know what to call it. But when you think about this choice here of the limits, isn't that really what's happening? That we're finding every x value from 0 to 2? Right? So when you think about x here, or the radius, like the radius is going to be any number from 0 to 2, which makes sense if the limits are going from 0 to 2, that the radius is actually just x. So here's the thing. This calculation should give exactly the same answer that Olivia gave us a minute ago. Try it. Let's look at another one of these. Okay, so I think it really comes down to this. So here's maybe something else to include in your notes. Do you notice that the rectangle, so when the rectangle was perpendicular to the axis of revolution, we're going to get a washer or a disk. When the rectangle is parallel to the axis of revolution, we get a shell. When the rectangle is perpendicular to the axis, that was the washer disk. When the rectangle is parallel to the axis, we get a tube, we get a shell. So you can really do either method, and sometimes you might choose one because it means you don't have to rearrange the equation, right? In that first one, we had to take the equation and solve it for x, which wasn't hard to do, but if it was harder, we could have skipped it by switching to the other method. Okay. I'll tell you right now that on this test, I am probably not going to say use a certain method. Now, I may make a problem that if you don't use the right method, you're going to get terribly stuck, but I'm probably not going to say you must use shell when you could think about it as washer. But I might give a question that you really can only think about shell because the solving becomes way too difficult. The radius. So it could be like the function is definitely going to be connected to the height, and x or y is going to be connected to the radius. It's possible that it wouldn't be the radius because it would be x or y if we're revolving about the x or y axis. But if I revolve about a different line, I can get an adjustment to it. And we haven't really seen that yet. I probably won't do that till tomorrow to like say, revolve this same shape about x equals -2, right? Something like that. So do you notice that I would have changed the radius if I would have done that? So we'll talk more about that. I don't think we'll go there quite yet. Okay. So again, if you're kind of thinking about the three-dimensional shape of this, like it's this stack of You could think about it in the washer method or the shell method, but either way, you can probably start to imagine what this shape looks like. Remember, it looked like a cylinder on the outside, so new problem. Here's our function, g of x, -1/2 times x minus 1 times x minus 4. I wrote it that way to actually make this really simple, to know that the x value here is 1 and the x value here is 4. Okay. I want this region that's sitting above the axis here, I would like it revolved about the y-axis. Okay. Now, let's pause for just a second. Let's pause for a second. Let's think about what it would mean if I did washers, and why this question is not a great question to think about the washer method. Possible, but you probably don't want to do it. Nene? Okay. It's already solved for y. You didn't mean that. Solve for x. And so I'm going to solve for x, and I'm going to end up with something with a root with a plus or a minus associated to it. Why is that? Because I'm having to think about it from the other perspective, which means one of these is going to be associated with like this distance here. So this would be like r little, and then r big would be from here to here. I can do this method. It's possible. You're going to have to multiply this out. You're going to have to think about rearranging it and then solving for x with the quadratic formula. It's a mess. So the suggestion then is maybe this is not the best method. So notice that that would be drawing horizontal things, perpendicular, right? There's that washer thought again, right? Washers here are not a good idea because right now it's one function that I'm going to have to split apart to get the left and the right side. Are you okay with the logic here of why? So if I gave you a question like this on the test, you should probably look at this and go, I don't want to do washers. Can you get the right answer? Yes. Will it take you longer? Yes. Okay. Shell is definitely a better thought here. So shell method, we're going to draw a vertical rectangle. There's our parallel pattern here. So step 1, there's my rectangle. Step 2, we tend to draw the cross section, but again, instead of trying to draw like the shell like this and then think about cutting it and folding it, what I usually just do is draw like the, you think about the three-dimensionalness of that cut and unfold. This thickness is going to be this thickness again. There should be a circumference and there should be a height. So can you write an integral? You should already know if it's dx or dy. Do you know the limits? There's going to be a 2 pi. There better be a radius. There better be a height. Work together on it. See if you can come up with an answer. Set it up. Put it in your calculator. Get a result. The radius is often x or y, but not exclusively. Don't think that it should be more the variable than the function, though. Okay. Okay, so a lot of people got to this part very quickly. It's the integral. It is dx. There's always a 2 pi associated with this, and just like the other one that I put the pi on the outside, I'm going to tend to put the 2 pi on the outside, just so it doesn't clutter up my integral there. So 2 pi. The radius. Well, the radius should be this in the drawing, right? It's from the axis still. That is definitely just an x value, right? So wherever I draw this rectangle, isn't the radius whatever x is? Okay, so the radius is x. The height of the rectangle, well, that's defined by the function. So again, it's perfectly acceptable to just write g of x there. Like you could write the function out, but there's no confusion here if I write g of x, so I can just put g of x. Definitely don't square it, right? This isn't the same. This isn't the washers where we're doing the area of a circle, right? This is that rectangular slab, that prism there. So lower limit is the controversy. The upper limit, though, is definitely 4. The lower limit, these are x values, is 1. Should it be 0? Why is that the controversy? I think people look at that's the axis of revolution, so they want to just say, so the lower limit is 0. So I'm going to say this another way. Do you remember how I was talking about the washer method? And I would say things like, it's the lowest value that we can construct a washer at. So what is the smallest x that creates a shell? It's 1. Now, if you would say 0, think about what you just did. Okay? This function, g of x, keeps going, right? So if you actually say the lower limit is 0, do you see that you're finding a very different shape? You would get all of this region that's also then spun about the y-axis. That's a very different shape than what we were talking about a second ago. Okay? So think about where the rectangles start and where the rectangles stop. The rectangles started at 1, they stop at 4, there's your limits. Put this in your calculator, it spits out an answer. I didn't write it down because I'm more interested in the setup. Okay, what was the answer? 45/4 pi. Okay. 3-dimensionally, what does this look like? The 3-dimensional shape. No idea what that means. Okay, do better. You figured it out yet? Hmm? Talk to your table. I don't know, I wasn't listening. What? That's my favorite answer. A bundt cake. What's a bundt cake? Bundt cake. You can go to that little shop right over on Veterans, like Nothing Bundt Cakes or whatever like that is. So yes, now does this have a hole in the middle? Definitely does, right? It has to have a hole in the middle because we're integrating from 1 to 4. So from 0 to 1, there should be a hole in the shape. So this is that pan. When you think about that pan, it has kind of a parabolic cross-section like to those pieces. And you bake it actually upside down. Those of you have no idea what I'm talking about. And then so you flip it over and you get a shape like this. So go get a bundt cake, make a bundt cake, think about calculus over spring break maybe. Okay. You're welcome. I think this is a good place to stop, so let me give a quick summary. Okay. This problem is a great example of shell method because we don't want to solve for x. Y is already solved for. If y is already solved for, that's going to kind of force our hand in terms of the integral. right? So that means that if I don't want to solve this for x, I have to think then dx. Well, the moment I think dx, I have to draw my rectangle vertically. And then I think about that revolution, and that's no longer a washer or a disk. I'm into the shell method. And so the shell method, we just have the components that make up the cylindrical shell. So again, we're thinking about the volume that we're talking about is the amount of, if I'm making the analogy to pipes, we're not finding the volume of water that the pipe can hold. We're finding the volume of copper needed to make the pipe, right? It's the amount that goes into the material to make the shape. So we're going to flatten it down into the corresponding prism that would make it. This thickness should correspond to the thickness of the wall, which is dx, and we're still integrating this area. So it's always going to have a 2 pi, an integral, a radius, times a height is what this shell method should be, okay? So with that, I do have for you just some extra practice as a packet here. I'm just going to have you grab one on your way out. Remember that by Friday is a quiz. It's like 5 questions over these kinds of things. When you get your packet, you're good to go. See you tomorrow.